when discussing functions, it's often good practice to use limits to determine whether or not a function is continuous. So when we think about continuity of a function, we typically think back to the way it was described in algebra, pre-calculus, where the graph of the function can be drawn in a single stroke without having to lift a pen off the paper. But mathematically, we want to think about this a little more rigorously. So first, let's look at three types of cases where a function may not be continuous, at least at a point. So if we take a look at this first graph, we have some graph of a function, but we have this hole here, this blue hole. And in that particular case, f is not defined at c. So we have a, b, and c here. F's not defined at c. What that means is that no matter what happens here, the function can't be considered continuous, because if I were, again, trying to graph that, I would have to miss one specific point, and to do that, it would be discontinuous. That hole really doesn't exist. We just sort of blow that up. But basically, the function has to be defined on a point for it to be continuous. The second one is that, okay, well, let's take into account a case where the function does exist at that point, but it also seems to make a jump. So you would draw it and you'd hit a point, but then you'd have to take your pencil off the paper and draw it again. So in this particular case, f of c is defined and it exists, but the limit does not exist, right? Because as we come towards this point, we come towards that point, we come toward two different limits, so those don't agree. And finally, we have a third case where, okay, it's defined, the function is defined at c, the limit actually does exist there, but the limit does not equal the function's definition. So if you thought about this, think like a video game. You're traveling along along, you have a good idea of where you're going, and then the game kind of glitches, and all of a sudden you're up here, and then you're back down. So traveling along, glitch, travel along, right? You have a discontinuity there. So the idea of a continuous function would be something simply where we go up and just smoothly go through. And to rigorously define those three criteria, we come and we say this. If the function's defined at a point, if the limit as x approaches c of the function exists, so there is a limit as the function approaches, or the limit of the function as the x value approaches that point, and third, and also important, that that limit is equal to the value of the function at that point, then we can say that the function is continuous, at least at that point. And that matters because you'll have functions which have gaps of continuity. Like, think like this could be a piecewise function, and it's continuous from A to C, and it's continuous from C to B, open intervals, but it's not continuous at that point, so you can kind of break it into gaps. So a lot of times it's important to discuss if something is continuous at a point versus being continuous generally speaking. But if we want to discuss the continuity on an open interval, and remember that an open interval is, if you have an A and a B, it uses those parentheses instead of brackets to say that we don't include the edges. So we don't include A, we don't include B. An open interval includes everything between A and B. So if we can prove that f is continuous at every point C, where C is between A and B, then we can say that it's continuous in that whole interval. And in practice, you don't pick every single point and go through it. We learn very special techniques that give us nice guarantees about continuity of functions.